Welcome back. Today we're going to be doing trigonometric substitution. Try saying that one time slowly. So today we're going to follow up with the previous video, which was all about not using trig and trying to use a simple u substitution. And now we're going to do a problem that does require trig substitution, and we're going to talk about why that is. So we're going to start with a very similar problem, but you're going to notice that it's missing one thing if you saw the previous video. The previous video, there's no x like we had then. And because of that, if we set up the u substitution, we won't have an x for the du. So we cannot use a simple u substitution. I also look at this, I say, well, can I expand it? And the answer is no. Radicals, especially radicals with minuses or pluses inside, they're really tricksy. There's not a lot you can do. And so I'm going to recommend something. This is going way outside the box. And so obviously I know where it's going. So when you see this, you're going to say, oh, why are we doing this? And the answer is, this is what you do when you see a particular pattern. And in this case, it's radical and then a subtraction with an x squared. If you see that, a number minus x squared, and it can be any number, then you know that you want to use a trig substitution. So let me show you what that looks like. Dun, dun, dun. So the trig substitution here is you let x equal 3 sine theta. And I know you're already saying, what? And I'm going to say, well, this is because we're seeing a particular pattern here. And so you can kind of guess, you can look at this and kind of guess and go 3, that has something to do with 9, right? That's the square root of 9, or the principal square root of 9, I should say. So I'm going to just tell you this is the way we want to proceed. And then what I'm going to do is show you how it all works out. Now, again, I just want to be very clear when I say this is not obvious. This is very complicated, and it's really easy to get lost in the details. So I really encourage you to practice this, do this in groups. Ask me for lots of help. Ask the tutors for lots of help, because this subject, it's challenging. You're not imagining things. It really is challenging. But let's give it a try. So the first thing is I'm going to say let x equal 3 sine theta, and then I gave restrictions on the domain. Normally we're kind of loosey-goosey with domains around here, but in this case we have to be very, very careful about it, because it is not just rewriting a simple, let's just let u equal, 4x or something like that. We're actually invoking a whole big fancy function, and this function is periodic, which means it is not one-to-one. So let me remind you, pardon me, Square Bear. Square Bear's here for all the square roots and the squares, of course. That's his favorite thing. So if I were going to draw a picture of the graph of sine, and I intentionally wanted to come up with a very bad picture of it, I would call me, because I'm really good at really questionable sketches. So we've got something that looks like this, and then it goes down, and then it comes back up, and then it goes down, and then it comes back up, and so on and so forth. So, and so not to scale, this should all be ending at 1. This should be our -1. This should be up at 1. So this is approximately what sine of theta looks like. I know we're doing 3 sine of theta, but just make it taller, and then it's 3 sine of theta. And you'll notice that if I draw a horizontal line, I see that there are many points, many different values of theta where y hits the same value. And that means that it's not 1, 2, 1. That's called the horizontal line test. It's like the vertical line test for functions. Basically, it's not a function when you try to go backwards. And what we're going to do is we're going to let x equal 3 sine theta, but then we're going to do a lot of work, and then we're going to go backwards. And the problem is if we go backwards and it's not 1-to-1, this all falls apart. So what we're going to do is we're going to restrict this. We're going to say specifically we're picking this spot. So we're going to pick from negative pi over 2 all the way up to pi over 2. Let me draw it up here. And as you see in this section, if we just pick this section, y never repeats itself. So in this section, between these two values, negative pi over 2 and pi over 2, we get just one piece. It covers all the values from y equals, negative 1 to y equals 1, but it doesn't repeat itself. Okay. So next question you should be asking is that legal? Can we just let x equal anything? And the answer is no. But when we look at this, we see that there's an interesting domain anyway. This domain has to be limited because if x gets too big, then 9 minus whatever x squared is won't be a positive number, so we can't take the square root. And again, is it possible to do math with imaginary numbers? Absolutely, but that's a whole branch, and we're nowhere near that. It's going to be a couple years before you take those classes. So for now, x is really limited with what it can be, and it turns out that 3 sine theta will model that really well. And if you have any questions, come and talk to me. We could do a 3-hour video, but I'm not going to. So I'm just going to say what I've said and say, this is going to work, and you can take my word for it, or you can come in and talk to me or talk to the tutors, and then we can have a whole trigonometric substitution party if you want. Okay, but for now, I want to go on with this, and I'm going to say if x is 3 sine theta, then dx, the derivative, is going to be 3 cosine theta d theta. Take a look at that. Do you guys agree? And then I have to figure out what this in here is going to be. So radical 9 minus x squared is going to be radical 9 minus 3 sine theta squared. Right, so far so good. Pardon me. And then that's going to be, and this is as we expected, 9 minus 9 sine squared theta, right? And then I can factor out a 9 and get radical 9. But when I factor out 9, this is going to be 1 minus sine squared theta. And then I'm going to remember, wait a minute. I know that sine squared theta plus cosine squared theta equals 1, right? And then if I subtract sine squared theta, I'm going to get cosine squared theta equals 1 minus sine squared theta. So I've got radical 9, radical 1 minus sine squared theta. So that's going to be 3 radical cosine squared is going to be 3 I don't know what happened to that s. That s is already a little nervous about what we're doing. 3 cosine theta, okay? And so that's really interesting because I end up with a nice cosine, which is really lovely. Okay. So I wrote out more of it here so we can go through. Radical 9 minus x squared is what I did here. And then I plugged in, remember we've got 2 parts. We've got the 9 minus x squared, which is going to be this piece, right? I'm trying to get all the purple pieces. And then also we have the dx, which is actually worked out pretty simply, and we're just going to stick that in where the dx is, right? So this is going to be, even though we're calling it fancy things, trigonometric substitution, we're actually just following the same rules that substitution normally follows. We're just, instead of making u be something simple, u, or in this case, x and theta, are much more complicated. Okay, so let's continue. I've got my dx. This is my dx part. And this simplifies, and I end up with 3 cosine theta, which is what I got right there, right? And then I got 3 cosine theta. So let's stop right there and look at that. Make sure you understand this. This is the yellow part right there. And this is the purple part right here. So I bring it all together and I get 3 times 3 is 9. So I bring the 9 outside and I've got cosine squared. And now we have moved into a slightly different problem, and that is that I don't have a formula for the integral of cosine squared. However, in the last video, we talked about integrating trigonometric expressions and formulas. And so we practiced with the half angle formula. Yay! And I wrote it down for you right here, just in case you've forgotten it. I frequently forget it, so I assume I'm projecting, I think, that you guys have forgotten it, because I certainly forget it all the time. I just know it's there and sometimes look it up. Shh, don't tell anyone. Okay, I'm a fraud. So instead of cosine squared, I'm going to write 1/2 times the quantity 1 plus cosine 2 theta, d theta, right? So this is exactly the same, or not the same, it's an equivalent expression, right? Okay, so far so good. So what did we do on this page? Because this is a lot. This is quite a journey. We started with x. There was no trig in sight, but because we have that square root, and again, if you've got a square root and a number and an x squared, that says trig substitution. Why? Because it does. We can thank dead mathematicians. This is how they worked it out. So we're going to do a trig substitution. So we did a trig substitution, and then we got to the point where we had cosine squared, which in the last section we realized, oh, we can't integrate that directly, so we'll use a half angle formula. Okay, so far so good. You guys are awesome. Remember, you can always pause the video, take a break, come back, or review things. So, oh, you know what? That was really mean of me. I thought I wrote it again. So let me write, we've got the integral, 9 times the integral of 1/2, 1 plus cosine 2 theta d theta. Sorry about that. Square bear, you okay? No, I'm great. Okay, so here's the 9, here's the 1/2. 1 integrates to theta, because we're in d theta land. We've got the c. And then the trick is, what is 1/2 sine 2 theta? How did it come from cosine of 2 theta? And so let's talk about that. Cosine 2 theta goes to the 1/2 sine 2 theta. Why? Okay, pardon me, square bear. I'm going to move you to the other side. Thank you. Oh, now you have to look. Yeah, you watch out for anyone who's going to come, because we're going to be very distracted right now. So if I take d theta of sine of 2 theta, right? What happens? Well, this is an outside and an inside. So this is the chain rule. I'm going to get the derivative of sine, so that's going to be cosine of 2 theta times the derivative of 2 theta, which is cosine 2 theta times 2. So I get an extra 2 popping out, and that 2 is not there. So to compensate, my antiderivative has to have a 1/2 in it that eats up that extra 2. Okay? And again, if that doesn't make sense, please let me know. You know, talk to me, ask lots of questions. I would love to explain it. Okay, now we're here. We've integrated. Oh my goodness, isn't this exciting? We're at the point of integration, and which I think is lovely because, right, that means to bring things back together. So what we need to do now is we're looking at this realizing, oh no, the original problem was not in theta. The original problem was in x. There were no trigs anywhere. So what are we going to do? And especially because x equals not sine of 2 theta, but sine of theta. So what we're going to have to do is to use the double angle formula to figure out how to come back to just sine of theta. Okay. So to convert back to sine of theta, not sine of 2 theta, we use this double angle formula. So sine of 2 theta is going to be this guy. So this is where that comes in. We've got the 9/2, we've got the theta, we've got the plus c, and then we've got this 1/2 times 2 sine theta cosine theta, which is really nice because this is going to be 9/2 times the quantity theta. Notice what happens when I've got 1/2 times 2. It just cancels out, and so we've got sine theta cosine theta plus c. Okay, now we're going to substitute back into x. And this is the point where you choose to use just algebra, or you choose to use a triangle. And what I'm going to do is I'm going to say this is going to be doing this all without triangles. So I'm going to show you this first way, and then I'm going to show you how to do it with triangles. Do I think there's a better way? No. I think that they're really different. And so in general, people tend to either be like, oh my gosh, the triangles are so much better. Or they're like, oh, the triangles are awful. Don't even, never. So it really depends on how your brain sees things. But up until now, there's pretty much just the one way to do it. So, right, we did this trig substitution. Then we manipulated what was inside the integral. Then we figured out how to integrate. Then we used the half angles and the double angles to kind of get everything to cooperate. And now we're to the point of substituting back into x, and that's when the triangles come in. But this first time, we're not going to use the triangles, so we'll do that. So remember that way back when, x was 3 sine theta. So sine of theta is x over 3, right? Divide both sides by 3. So theta is arc sine, which you can also write as this, right? It's the inverse sine of x over 3. So now, okay, we do not have sine by itself. We have 2 sine theta cosine theta. We know that sine of theta is x over 3. So what is cosine? Well, cosine theta is the square root of cosine squared. Stay with me, stay with me. I know you're all like, wait, what? I squared it and square rooted it, trust me. Cosine squared is 1 minus sine squared, right? Pardon me. I guess I'm allergic to this. And that's equal, there's sine, and we know that sine is x over 3, so it's x over 3, the quantity squared, in place of sine. So we've got this expression, 1 minus x squared over 9. Okay, so here was our answer, our original answer. And then I said, oh, these two can combine. So then we just get sine theta cosine theta. And now let's resubstitute back to x by saying theta is arc sine of x over 3. That we found up there. And then here is sine theta is right there, and there's cosine theta. And so that is wholly unexpected, right? Because if you can, let's see if I can get back to that very first page. If you start out with a problem, scooch, can you see it? Kinda. When you start out with a problem that looks like this, and you say, okay, what's the integral of that? There's no mention of trig at all, and yet the integral has arc sine in it. You can't actually completely come back to x and leave trigonometry land somewhere else. So, wow, that's surprising. Now, what am I doing here? Oh my goodness. So let's look at this last step. I've got arc sine of x over 3 plus x over 3 times this thing. And of course, as mathematicians, are we going to leave that alone? No. Let's see what we can do about making that a little bit better? Question mark. So here we go. Follow me. Follow me now and believe me later. Here's arc sine x over 3 plus x over 3 times, and then this used to be 1, and I'm rewriting it as 9 over 9, okay? And then I'm not touching this. You can see all the way through, not touching this. So really, we're just focused on this part. So then I factor out, see the ninths in both, I factor out the 1 over 9, and I get 9 minus x squared. There should be one more parenthesis there. Sorry about that. And I pull out the 1/9, and the 1/9 when it comes out is 1/3, because it's the square root, right? And then that becomes x over 9. And then I've just got the 9 minus x squared inside there. And then the last thing that I do is I multiply through the 9 halves, and the 9 halves and the x over 9 cancel. So I just get 1/2 x, or this could also be x over 2 if you'd prefer. Yes, my cat is like, really? You're doing trigonometric substitutions when you could be playing with me? And the answer is yes, I am. I am doing that, but I will play with you. So, okay, she's coming to join the video. Oh my goodness. Okay, not right now, sweetie. Not right now. Hola. I love you very much. You just sit right there. There you go. Yeah. Okay. As far as she knows, I'm saying all of this to her. So, next up. No. Okay. Yeah, maybe. Okay. Next up. Well, first up, do we have to do all of this work? I mean, I think technically for what WebAssign wants, so if you're talking about your homework, you don't need to do it. I don't think you have to go through all of this. Was it a legal, nice thing to leave here? Technically speaking, there's a fraction. And if there's a fraction, then you can't have it inside a square root. So all of this was an attempt to resolve so there's no square root of a fraction. So is it required? Math requires it. Will your homework require it? Probably not. Your homework will probably count it as correct, even if you don't. It's called rationalizing the denominator. But if you're doing, math for somebody, and somebody's actually a human's gonna look at it, you probably should. So this is a choose your own adventure moment. So now, you don't need that other page. That other page is the next video. So let me hide that. No need to worry about that right now. What I do want to talk about is 2 more things. Are we allowed to do this? Yes, as long as we limit theta so that x equals 3 sine theta is 1 to 1. Remember we talked about, I drew a little graph and I said stay in between these 2 spots. And this is an inverse substitution, the way it works. So, the next question. I know I've got a table down here. You guys are like, wait, let's see the table. Tables are cool. I agree, tables are cool. But first, what I would like to do is I would like to do the whole thing that we just did, but do it using triangles. You know what? I've got it written out. So I'm just gonna cheat. I did it ahead of time, and through the magic of television, I can just use this. And let's just talk about it. That way I'm not worrying about drawing any pictures or anything. Okay, so here's the triangle method of doing this. And I want to remind you that if I have a right triangle, that the square of the lengths of the legs, that sum is going to give you the square of the hypotenuse. Or if you're looking for a particular side, what you do is you take the hypotenuse, the square of the hypotenuse minus the square of the other leg, and you square root it, right? So this is the Pythagorean theorem or the Pythagorean theorem. And so this is going to come up, as you recall, I said without triangles. So you've already done the integration, and now you have to rewrite this back into x. So when you're translating back into x, instead of doing all of this, you can use the triangles instead. Okay, so let's talk about that. So if I have, as I did, x equals 3 sine theta, then x over 3 is sine of theta. Now I also know that sine of theta is opposite over hypotenuse, right? So what I can do is if I set theta here, here's opposite, here's the hypotenuse, I set up this triangle x over 3. Am I allowed to do this? Yes, absolutely, because we've got all sorts of interesting stuff that has to do with similar triangles. But I need to figure out what this length is. So I put a box there, you could put a letter there. I figured we've had so many variables at this point, I would just keep it visual. So box squared, the unknown thing squared, plus x squared is 3 squared, right? So box squared is 3 squared minus x squared. That's 9 minus x squared. And so the length of the box is the square root of 9 minus x squared. Now I want to stop there, make sure that all makes sense. And then I want to find the very first page and ask you, what was the integral? The integral was radical 9 minus x squared. So right there, we already had this form that is already speaking to a right triangle. So that's why it wasn't completely ridiculous that someone came in and said, hey, let's use sine and cosine. So this is our new triangle. And so what is cosine of theta? It's adjacent over hypotenuse, which is radical 9 minus x squared, right? We already figured that out, over 3. Now, did that save us any time? So remember that we said that. Oop, that's not the part that I want to show you. So then let's go back over here. Remember without the triangles? We did all this without the triangles, yada, yada. And I said, what is cosine? Cosine of theta is this, and all of this. Oops, which is 9 over 9 minus x squared over 9, which is 1/9 times 9 minus x squared, right? Which is 1/3 times 9 minus x squared, which is radical 9 minus x squared all over 3. So what are we talking about when I say without triangles? This is what you get to using algebra, if that makes sense. Or if you set up a triangle, this is what you get to for cosine. So, and you get the same answer. So you can either construct it using triangles, which a lot of people look at and they're like, oh my gosh, this is the best thing ever. And then other people are like, what? I don't want to draw pictures of triangles. I just want to use algebra. So it's totally up to you. And this is the section I'm going to write can use triangles here. This is the section where you would use triangles when you're trying to figure out what cosine is. Or if you're trying to figure out what tangent or secant or any of the others, you can use triangles for these. So this is the only part. When I say triangles or no triangles, it's a very small part of the problem, but it is a crucial part of the logic. And you get to choose sides, or you can just, you can be chaotic good and just run around doing it whichever way feels like in the moment, or, however you want to do that. Woohoo. So it's a very long video for just one problem, but I have one more thing I want to share with you. And the one more thing that I want to share with you is that this is a table that's in your book, and now it's in your notes. And that is that we did an a sine theta. We did 3 sine theta because we've got the a squared minus x squared construction. But that in fact, if we had plus in the middle instead of minus, oh, here's Chai again. Chai loves, I don't think she's enjoyed math quite so much as she has today. So it turns out trigonometric substitution, it's a great way to make your cat happy. She's just going to wag her tail and pretend like it's no big deal, no big deal. Okay, so I got to wrap this up quickly or the world will end for one very small, very sweet cat. So, but this table tells you where you should start. And the way we start, and this is a random collection, I know if you're trying it, sine, tangent, or secant, which are unexpected, like why not cosine? These are set up so the derivatives are nicer and you don't have to deal with as many negative numbers if you can help it. But you are welcome to try other substitutions because there are other ways to do these. These are just the recommended ones. And since they're already worked out for you and it tells you where theta needs to be and it tells you the key identity you'll have to keep in mind. So it's a nice little table. So this will be in your notes. And that's it. Oh my gosh, you guys. You and I and Chai have made it through this video. I am so thrilled. I can tell you now, I've tried to record this like 5 times already, and it's just been a disaster. So thank you for the patience you didn't know you were giving me. And I am thrilled we made it through and without any disasters. So go out. I don't know if it's raining or sunny, but give your eyes something else to look at. Maybe touch some grass. Pet Chai, because she really desperately needs it, or else the world will end. And know that I'm really, really proud of you. And it's absolutely reasonable and expected and encouraged for you to be reaching out for help with these, because these are, I don't know that they're anyone's favorite. They're pretty challenging. So take care of yourselves. Be gentle with yourselves. And math on. Woo.